start recording. I wanted to go through some admin stuff. So these are going to be two quick points about admin. The first one is that I posted a supplementary note about the induction proof that I had to skip on Thursday. So please do check that out, because in assignment 2, there's going to be some induction questions, and looking at the notes is going to help you know how to solve that. There's also induction videos about those supplementary notes, which I also posted. So in case the notes aren't enough, you can also watch a video where I explain to you what I'm doing. Okay, the other thing, so that was about, I guess, all right, induction. The other thing is I've already gotten some emails and people who come to office hours who are worried about the evaluations of the class. So they come to me and they're like, Cesare, I don't usually do proof-based classes and I'm very worried. And to them, I say, don't be worried. So please don't be worried. There's several reasons for you not to be worried. So the first thing is that I know how you feel. I've also been a student and I know how stressful things can be. So the goal of this class isn't to stress you out. It's to expand your minds in some way, shape, or form, right? And to sort of alleviate some of that stress, what I'll be doing close to the midterm is I'll be posting a sort of midterm preparation guide. I'll also do the same thing for the final. So I'll tell you what exactly to study from the notes, and also post some review exercises for you to practice. And the other thing is I'll tell you more or less what's going to be on the midterm. I won't tell you what the question is, right? I'm not an idiot, but I'll tell you, you know, there's a very nice question about DFAs, and so practice designing DFAs. Okay, so do people feel less stressed? Okay, one person, good, excellent. So no one else was stressed, that's good. Okay, so let's get started with the actual material. So I guess I'll just write, this other point was about being less stressed. Okay, so just a recap of what we've been doing so far. So, you know, we started with some math review, we did some formal language theory. So, right, we studied languages. Okay, we spent a lecture on it. In computational linguistics, you spend 2 or 3 lectures on it. And then last class, we started talking about our very first computational model, which was known as the DFA, right? So the DFA, the deterministic finite automaton, is a computational model which has a finite number of states and is deterministic. And we'll see sort of more clearly why we say that the DFA is deterministic and what it means for something not to be deterministic today. And the one thing that I also want to point out that we talked about on Thursday was the notion of regular languages. So this was a definition that I gave a bit too quickly. And so I think I just want to quickly talk about it again. So regular languages are family of languages. Okay, so if you take the family of regular languages, there's languages in here, right? So, you know, maybe this is a language, maybe it's AN, where N is greater or equal to 0. There is maybe a finite language like ABA. We'll see in a second that sigma star is regular. Okay, so there's a bunch of languages, right? So it's a family of languages. So it's a set of sets, really. But just because sets of sets sounds a bit redundant, we say family of languages. So DFAs essentially allow you to show that a language is regular. So if you can build a machine M, which is a DFA, which accepts that language, then you've shown that it's regular. And we saw at the end of Thursday's class how you can prove the correctness of a machine M. Okay, and so today what we'll be doing is we'll be looking a bit more on DFAs, so more on DFAs. And we'll also be introducing their cousin, the NFAs. Okay, and I think for the rest of the week, I think we'll just talk about NFAs and maybe closure properties. Okay, so that's where we're sort of headed. Now what I'd like to do is I'd like to give you a warm-up exercise. So I'll call this a warm-up. Whoa, a wham-up. Okay, so suppose the alphabet is AB. The question here is, which of the following languages languages are regular. Okay, and I'm gonna write 3 languages. I have L1, which is the empty set, L2, which is the set containing the empty string, and L3, which is sigma star. Okay. So the question is, which of these languages are regular? So really, effectively, what I'm asking you is, which of these languages have DFAs that accept them? Okay. So let me give you, let's pause. Let me give you like 10 seconds to think about it. Okay. So what do we think? Any takers? Yeah, in the back? All of them. Oh, all of them. Why do you say all of them? I'm surprised because you got it right.
Should I explain like what the machine?
Maybe I'll take over. Yeah, so it is correct. It is all of them. All of them are regular. Let me show you why. Usually people sort of, the reason why I think this is a good warm-up exercise is people often think that these languages are very special, and because they're special, they're somehow not regular. That isn't the case. So for instance, if the language L1 is the empty set, and I'm trying to accept this language, right? Remember, the empty set is a set. It's a set which contains no strings. So how can I create a DFA which does not accept any strings? Well, that's pretty easy. I have a start state, right? And now whatever string I get, whatever string my machine gets, it's just going to gobble it up and reject it. So then to do that, I just have a self loop. And my start state is my only state. It's not an accept state. So if I start with any string, like if I start with ABB, my input string is ABB, then my machine is going to read through the symbols of the string, and it's just going to stay in here, right? And this state is not an accept state, which means that it gets rejected. The string gets rejected. Yeah? Okay, good. So what about, let's do L3 second. So L3 is kind of the same idea. I gobble up all the strings, but now instead of gobbling up and rejecting them, I gobble them up and accept them, right? So I do the same thing, except that my start state is now an accept state, right? So I just accept everything. Yeah? Any questions about this? Because people look confused. So please ask questions. No questions? Oh, sorry. Yes.
I kind of forgot what regular means. Does it only mean that I can build DFA for the language?
For now, a regular language is a language where there's a DFA that is that. So that's why so far both these languages accept them. Because there's a DFA. Yeah.
For the empty one, L1.
Yeah.
Are you accepting the empty?
No, that's a very good question. Okay, so that's a good transition to L2. So the question was, for L1, isn't my machine accepting the empty string, right? So that's not the case. For DFAs in particular, the only way for a DFA to accept the empty string is for the start state to be an accept state. Okay, and the reason for that, right, is imagine the input string is the empty string. Then my machine starts to read it, and it sees, oh, it has nothing to read, right? So it just starts at the start state, and then it just stops, right? So because it stopped in the start state, and the start state is an accept state, then it accepts the empty string, right? But now, if X is not the empty string, then ideally, because we're talking about L2, you'd like to reject all the other strings. And so to do that, I just take any other string, and I garbage collect it. Okay. And that's a machine for L2. Yeah. One more question. Yeah.
So like,
Yeah.
now given that L1 and like L2 there are different pieces, what's like the
Excellent question. Yeah.
what's like the ontological difference between
Okay.
string and string or something in it?
I thought you were going somewhere way different. Let's take that offline. Let's take that offline, okay? I thought you were going for, oh, there's many machines that you could create to accept this language. And so how do we sort of talk about the minimal machine, which is what I want to talk about next?
Yeah.
Yeah. I think I'll, okay, one more question. Yeah. The DFA for L1 doesn't have an accept state because L1 is the empty set, right? It's the language that contains no strings. And so you don't want your machine to accept anything, right? But accept states are there to accept strings, right? That makes sense. Yeah. So I'll take more questions after. Okay. Okay. So, the thing I wanted to talk about next was this notion of minimality. So the idea is, and this is sort of just a recall on the lesson of designing DFAs, is that when we design DFAs, so when designing DFAs, states should encode information. Right, so recall from lecture 3, we had the very first DFA that we saw was a parity bit checker. And so we saw that there was two states. One state was there for checking odd number of ones, and another one was there for checking even number of ones, right? So states should serve purposes, and those purposes are information that they encode, right? Because the states are sort of acting as the machine's memory, okay? And so the natural question that sort of follows is, what happens if we don't carefully design our DFA? Well, then if we don't, we may run into redundant states. Okay, so if we don't carefully design our DFA, then we may produce redundant states. So in other words, states which encode the same pieces of information. So if two states are doing exactly the same thing, right, they're remembering exactly the same piece of information, then probably one of them is not necessary. And so we have some redundancy. And the idea is, well, we'd like to get rid of that redundancy because we want to talk about the sort of canonical minimal DFA. So for example, what's an example of a redundant machine, so to speak? Suppose I have this machine M that looks like this. Okay, so what is the language accepted by M here? Yeah, Louis? Sigma star, very good. So the language accepted by M here is sigma star, right? It accepts, so assuming that the alphabet is AB, right? Whatever this machine gets, whatever input you give it, it doesn't matter what the string is. At some point, the machine is going to terminate, right? Because we're only talking about finite strings. And then once it terminates, it's either going to end up in here or in here. In either case, those are accept states, and so it accepts the string. And so whatever string you get, you accept it, right? So this is a machine M, which accepts sigma star. But clearly, this machine has some redundant pieces of information, right? Why is that clear? Because we just saw, right? We just saw another machine here, which also accepts sigma star, but this one has one state, right? So clearly, this guy is doing sort of, its states are encoding the same information twice, right? So in other words, M has redundancy, or the more technical term to say this is M is not minimal. M is not minimal. Okay. So now what I'm going to do is I'm going to define sort of formally what the notion of minimal DFA is, and then I'll show you how you can prove that a DFA is in fact minimal, which is one of the questions on the exam. Okay. So let's give you a definition. So this definition is for minimal DFA. So given the DFA M, we say that M is minimal. So let me underline minimal. If there does not exist, right? So this is exists, and the slash is to say there does not exist a DFA N such that, so ST is such that the language accepted by N is the same as M, and N has fewer states than M. Right, so this, I feel like this makes sense. You're saying some machine M is minimal if for whatever other machine you take, if that machine accepts the same language, it can't have fewer states than M. So that's the definition. So for instance, right, so just to make this super clear, for example, if we take M as this single state automaton, then this machine M is clearly minimal because we can't have DFA with no states. Well, let's not get into that because there is no machine that accepts sigma star which has less than one state. I'll say that like that. Yeah, give me 1 second. So it's minimal with respect to sigma star. Yeah, question. Yeah.
I don't think multiple minimal DFAs.
That's a very good question. The question is, can a DFA have multiple minimal DFA? Very, very good question. So the short answer is no, it cannot. Minimality is unique for DFA, but it takes 2 lectures to prove that. And so we'll do that in a few weeks from now. But that's an excellent question. Other questions about the definition or minimality in general? Yeah.
Yes, so the values and the given member state, the transition function.
Yeah, it's only about the number of states. Yeah. Minimality is only about the number of states. Other questions? No? Okay, good. All right. So now let's look at another proof technique. So we saw one on Thursday about proving the correctness of a machine. This is going to be another proof technique. So what I'm going to do is I'm going to give you general instructions for how to prove that a machine is minimal. And so like any algorithm that you foresee, it's going to seem like gibberish. So don't expect to completely understand it once I write it down. You'll have to see the example for it to make a lot of sense, right? For it to make sense. So the proof technique, with that being said, so how do I prove that a machine M is minimal? Well, we're assuming the question is something like, give a minimal DFA for this language, or that accepts this language. And so, of course, the first step is, of course, you need to construct the minimal DFA M. And suppose M is, Q, sigma, delta. I'll say the start state is Q0 in this case, and the accept states, right? So you construct some minimal DFA. And so remember, when you want to construct the minimal DFA, you want to be as careful as possible when you design your machine, right? So you have to make sure that each state should encode a unique piece of information. Unique and also not redundant. So unique and not redundant, because those two things aren't necessarily the same. Okay, so that's the first thing you do. So you build this machine M, and you look at it a bit, and you're like, oh, okay, this looks minimal. And so how do you actually prove it? So how do we actually prove that M is minimal? So to argue that M is minimal, you need to do a few things. The first thing you need to do is you need to say, okay, well, consider some arbitrary DFA N. Right, so consider some arbitrary DFA N. What you're going to want to show is you're going to want to show that for any DFA you pick, so you pick this one, this one, this one, this one, you can never create a DFA which has a smaller number of states than the machine you started with. Yeah, give me a second. So how do you do that? The trick is you're going to need to find, so you're going to need to find cardinality of Q, number of strings, using the original machine M. Okay, so that's the second step. Again, it makes sense. If this doesn't make sense to you at this point, you need to see an example. but you pick some strings, you pick some strings based on M, and the hint on picking strings is each of these strings should go to different states in M. And the final thing you do is you argue that each pair of strings, so that each pair of strings must go to a different state in N. Oops, different state in N. So you say, consider some arbitrary DFA N, pick some strings, imagine that each of these strings go to a state of the DFA N, and then you just argue that each of the states that those strings go to can't be the same. And so effectively, you've shown that the lower bound on the number of states for any machine to accept the language that M accepts is this guy, right? Is the cardinality of Q. So that's effectively what you've shown. Yes, there was a question. Yeah. I didn't get the last part. Oh. Okay, I see. So, okay, the question was, what do you mean more specifically when you say information, when we talk about DFA, right? So, when I say information, I'm sort of trying to get to your intuition, but really, sort of concretely, it's about what each state is supposed to remember, right? So, in the first machine we saw in lecture 3, there was 2 states. One of the states remembered the parity of, one of the states remembered that it saw an odd number of ones, and another state remembered that it saw an even number. So that's really what I mean by information. I mean this is a small piece of memory that you need for the machine to work out. Yeah, that makes sense. But it is an intuitive sort of term. Yeah. Oh, yeah. What's before that? Oh. After which one? Argue that each pair of strings must go to a different state in it. Other question? Yeah. Very good. Excellent question. Very good question. So the question was, well, why do I need to go through all this stuff? Why do I have to talk about some arbitrary DFA N? Why can't I just argue on N, right? I just built N. Why can't I just say, oh, N is minimum? Clearly, I can sort of break it down into more states, into a smaller number, right? That's a good question. The reason for that is because you want to argue on arbitrary DFA. So the machine you just built, maybe that machine you can't break it down, right? But maybe someone else could have built another machine where you could have broken it down. Right? That's it. Okay, last question. Need at least like 500. Right. So you don't, strictly speaking, you don't need N. N is just very helpful for finding these pairs. Yes. Good question. Okay. All right. Let's actually look at an example so this makes more sense. Okay, so the example here is going to be design a minimal DFA M. Thank you. Such that the language accepted by M is the set of strings of the alphabet AB, where the number of A's of W mod 3 is either 0 or 1. Okay, so this notation here just means, this notation means the number of A's in W. Okay, so this is what we want to do. We want to first design, we want to design a minimal DFA M such that that machine M accepts this language. And I forgot a curly bracket. So there we go. Okay, so the first part shouldn't be too bad, hopefully. So I need to design a DFA. And it has to be minimal. So I need to design a minimal DFA to accept this language. Well, let's see. What is the essential piece of information that I need for my machine to work? It's a question for you. So what piece of information do I need for M to work? Yeah. The number of A's, something, something. Mod 3, yeah. The number of A's mod 3, right? Because if you were just keeping track of the number of A's, then that would be hard because you can have any number of A's, right? So then you'd get into an infinite machine, and that's no bueno, right? So instead, what we're going to do is we're going to keep track of the number of A's mod 3. So I'm going to have one state here. See, does this work? Oh, cool. Whoa, oh no. Okay. The number of A's mod 3 is equal to 0. Then I'm going to have, whoops, no. The number of A's mod 3 is equal to 1. And then the number of A's mod 3 is equal to 2. Right, because there's only 3 possibilities. So where's my start state going to be? What's the start state in this case? 0. Yeah, someone said 0. So it's 0 because, if I have the empty string has no A's, no B's. So 0 number of A's mod 3 is 0, right? So it makes sense that I would start here. And now you'll notice that if I read B's, right? If I read B's, this doesn't change the modularity of the number of A's, right? So if I read B's in any of the states, then this stays the same, right? Then I stay at the same state. So the only thing that's actually changing the modularity is if I see an A, right? But we know that modularity in general is cyclic, right? So if I have the number of A's mod 3 is 0, and I read an A, then that means that my number of A's mod 3 becomes 1, right? So this is just basic elementary sort of number theory. Yeah, I'll get to you in a second. Okay, so now I'm at the number of A's mod 3 is 1. Now I read another A. If I read another A, then I get my modularity is equal to 2, right? Okay, and then again, I read another A. So if I read another A, then my modularity cycles back, and I start again at the number of A's mod 3 is equal to 0. And so now the only thing that's left, right? Because at this point, this machine is just sort of a sophisticated machine that accepts the empty set. So I actually need accept states, right? And so where are my accept states going to go? Yeah, Owen, yeah. Yeah, excellent, very good. So my accept states, geez, are going to go here and here, right? Because what I care about is accepting strings that mod 3, that their number of A's mod 3 is either 0 or 1. And that's these guys. There was a question, yeah. You have to have a mapping for every letter in it. I think you mean like if you have a state, do you have to have like A and B? Yeah, you do. Yeah, so that's one of the characteristics of a DFA is that this is sort of obligatory. Yeah. The other thing is that you can only have a single start state. Yeah. So there's no guessing allowed, basically. Okay. So this is a DFA, and I think it's minimal. And so I'm going to argue to you that it's minimal. I'm not going to give you the full proof, otherwise we'd spend like 20 minutes. But I'm going to give you a third of it, and then the rest should be self-evident. Also, yeah, I'll post something so you can see the rest. Okay. So how am I going to argue that essentially any machine, any DFA is going to need 3 states to accept this language? So remember what I need to do. I need to first consider some arbitrary DFA. Let's call it N. And let's suppose, right? Let's just suppose that the language accepted by N is equal to the language accepted by M, right? So this is like step A. Okay. So the DFA N is a machine. It accepts the same language as M, right? So, maybe N is this box here. Maybe it has some states. Well, it has to have states. So maybe it has, state A, state B, state C, and, so on, right? And so now what I care about is taking some strings from my initial DFA and then saying, okay, well, suppose each of these strings go to a state in my DFA N. And then I have to argue that those states have to be different. So how can I do that? Okay, I've been asked not to write on the line. Let me try make an effort not to do that. So I need to pick strings, right? And the trick behind picking strings is I want to pick strings that go to different states in my machine N. So in this case, what I'll do is I'll pick the empty string for this state, A for this state, because A goes here, right? And then AA for this state, because AA goes here. So I'm picking 3 strings, right? I'm picking 3 strings because, and each of those strings go to a different state in my machine M. Okay, so I'll pick W0 is the empty string, W1 is A, and W2 is AA. And next, what I'll suppose is I'll say, well, suppose W0 goes to A, W1 goes to B, and W2 goes to C, right? So the idea at this point is I don't know whether A and B are the same, right? Maybe these are different states, okay? Or maybe I just named the same state twice. So maybe it was the same state, I called it A first, and then I called it B second, okay? But maybe it's the same state. So what I want to check that each of these 3 states, that receive W0, W1, W2 as input, right? Each of these 3 states are distinct. So how can I do that? So now what I need to do is I need to argue that A is different from B, B is different from C, and C is different from A. So now you see why I'm just going to do a third. I'm just going to do this guy. Okay, so let's argue that A is different from B. So because I'm trying to argue that something is not true, what I'm going to do is I'm going to assume that it is true, right? I'm going to do a proof by contradiction. So the proof by contradiction is going to assume that A is the same as B, right? So in other words, these 2 states actually are the same. I just renamed the same state twice. So what that means, right? What that means is in my machine N, right? Remember, I'm talking about the machine N. I have some start state, let's just call it S0. And I have a string W0, which goes to the state A. And I have a string W1, which also goes to the same state B, right? So I'm assuming that A is the same as B. So now we need to find a contradiction. So what's going to be the contradiction? Does anyone have an idea of how I'm going to contradict myself? No ideas? Yeah?
Well, W0 should be in accept state, W1 should be in non-accept state, and you can have an accept.
Yeah, very good. Excellent. Yeah. So I'm gonna slightly generalize that argument, but yeah, that's very good. So what I'm going to do, because this argument is going to be useful to talk about in the future, is I'm just going to say, well, I know that these 2 strings go to the same state, right? So now suppose I read an extra piece of string X, right? So I read an extra piece of string X, which means that because A and B are the same, right? W0X and W1X should go to the same state. Okay, and now I'm going to argue that this is impossible because W0X will be accepted and W1X will be rejected. So this is impossible because a state can't both be an accept state and not an accept state. So I need to pick then an extension. I need to pick a sufficiently correct, well, a correct extension, not sufficiently correct. So how am I going to do that? Well, now let's suppose that X is equal to A, right? So here, this extension of the string was A. Okay, so now I have 2 new strings. I have W0X, which is W0A. Well, what was W0? It was the empty string. So I have the empty string A, right? So W0X is A, which means that in my DFA N, A goes to the same state as this other string, which I'll talk about in a second. So what's this other string? W1x. So W1 is A, and X is again A, so I have AA. So now from the start state, I know that A goes to the same state as AA. So now we have a contradiction. We kind of already did have a contradiction, as someone just pointed out. But now the contradiction here is that this is impossible. Since the number of A's of a single string of a string containing just one A is 1, and 1 mod 3 is 1, right? So then by definition of the language, that should be accepted, right? But then the number of A's of AA, that's 2, and mod 3, well, that's 2. And so by definition of the language, that should not be accepted, right? So in other words, this A should be accepted by the definition of the language, and this string should not. But that's impossible because I just said that these two strings go to the same state, right? So essentially it's as if it's as if the machine N is both a not accept state and an accept state at the same time. So that's the contradiction. And so then we just have to repeat the same procedure for the other two pairs of states. So we just repeat this. Right, so these three states have to be distinct. So in other words, the lower bound on the number of states in some arbitrary DFAN is 3. And so that's shown that M was in fact a minimal DFA. Yeah, question.
The only way to show the different states to consider moving from one state to another, like you just did? Or is there a more direct approach to showing the different?
This is pretty direct. Yeah.
But is this the only?
So there's other ways. Sometimes there's acceptable ways of arguing about the intrinsic architecture of a machine. Like suppose the language had to have strings of at least length 2, then of course you need 3 states, right? Because otherwise, how are you accepting the? Well, that's not entirely true, but so what I said isn't entirely true actually, but sometimes you can argue about the architecture in general, and then that's sufficiently good, but this is sort of like a foolproof method. Yeah, so for assignment 1, please use this method. Okay, it's just to make grading easier. Yeah. Yeah, which makes sense, right? Because the strings go to different states, right? That's why I was able to get a conflict. If they were going to the same state, then I'd be unable to get a conflict. Yeah.
Is this sort of form the picture?
Yeah, this is good. Yeah, this is sufficiently written for me and yeah.
In this example, for these P is not equal to A contradiction proof.
Yeah.
Those two strings that we take as examples, one of them is already going to be accepted, the other will already be rejected. So we have to add a extra students right away.
Yeah, no, that's a good point. So yeah, if you're in a situation where you're comparing 2 strings and one of them is accepted and the other one is not accepted, then you can just say, well, extend it with any string. And then of course you have a contradiction. Yeah. Okay, one more question. Yeah.
But completeness in the case of this group, we also have
Do you have to suppose that X is equal to?
I think this case, that we are going to
No. You just have to find that there's one string where you get a conflict. So yeah, one string is sufficient. Okay, good, excellent. So I think we can. Wow, I'm on time. Amazing. That never happens. Okay, good. See, I wrote 9:15 on my notes and it's 9. Okay, anyways. I think that's cool, but okay. So let's move on. So this is sort of the end of the DFA chapter. I will, like I said, post review exercises so that you can practice designing DFAs. The assignment is also pretty good for that. But don't worry too much about the other evaluations of the course. Okay, you'll be okay. Right? Okay, good. So the next thing I want to talk about, wait, maybe people have not finished writing. No, you have. Yeah. Okay. So the next thing I want to talk about is non-deterministic. Whoops. Finite automata. Okay. So so let me just write a small paragraph here. So in DFA, we would say that the behavior of the machine of the DFAM is uniquely determined by the state it's in and the symbol it's reading. So in other words, you know exactly what the DFA is going to do if you know what state it's at and what symbol it's reading. Okay, that's kind of what we mean by determinism in this case. So another way of saying this is DFA don't guess or make choices. Okay, their behavior is determined, right? It's deterministic. So now what happens, essentially the question, as computer scientists, let's ask the question. What happens when we give an FA, right? So a finite automaton, right? Multiple possible choices. So when we give an FA multiple possible choices, that's when we start to talk about non-determinism. So the behavior is not deterministic. And so what I want to do first is I want to give you a rather informal definition of an NFA. So that's what I'll do here. So an NFA is a computational, so comp for computational, machine, which is similar to DFA. So in other words, it's similar in the sense that it takes input strings and it returns either accept or reject. Okay, so that's how it's similar. The way that it's different is, so it's similar to a DFA, except that it is allowed to have 0 or more. And I'll call these very loosely transition choices. Choices. Yeah, I'll just end the sentence there. Yeah. So just by the way, that's the acronym NFA is just the acronym for non-deterministic finite automata. So let me illustrate that. The way that these machines can have choices is sort of twofold. The first way is that they can have multiple start states. So you can have multiple start states. So you can have maybe one start state here, another start state here, another start state here. And these machines don't have to be connected. They could be disconnected or they could be connected. Right? So you can have multiple start states, or you can have multiple transition choices. So in other words, you can have some state where if the alphabet is, say, AB, you have several possibilities. So you can go here, you can go here, you can maybe go here, right? So you have choices, right? And so that's kind of what we mean by non-determinism. The behavior is no longer uniquely determined by the state you're in and the symbol you're reading, because now the machine has choices to make. Okay, so now let's consider an example. Let's consider an example. So consider the following NFA N. So this is going to introduce you to the notion of multiple start states. So I have this first start state here. Whoops. So the alphabet is 0, 1. That's why I said whoops. I wrote an A. Oh, okay. Okay, so this is the first machine. And I have another start state here, which looks like this. Okay, so this is my second machine. Okay, so what you'll notice actually is that these two pieces are just regular DFA, right? And in fact, this DFA hopefully looks familiar. This DFA is from lecture 3. So I'm doing a lecture callback. Okay. I got one chuckle. Good enough for me. Right, so I have one DFA here and another DFA here. And so essentially now what's going on is my NFA has the ability to choose where it starts. Okay, but in general, an NFA can have any amount of choices to make. It just for illustration purposes, I'm just saying in this case, it can choose where it starts. So now what happens if it actually reads a string, right? So suppose as input, it receives the string 1001. So what's going to happen? Well, now, right, the behavior is no longer deterministic. So I have to consider all possible choices. Like, what can my NFA do? Well, what it could do is it could say, well, today I feel like I want to start with Q0. And so that's what it does. It starts with Q0. So it starts at Q0, and then it reads a 1. So it goes to Q1. Then it reads a 0. So it stays at Q1. Then it reads another 0. So it stays at Q1. Then it reads another 1. And it goes back to Q0. So Q0 is not an accept state. And so in this case, for the machine M, this is a failed computation. Okay, so this is the failed computation. So the NFA is sad. So what it'll do is it'll say, okay, well, this didn't work out. So let me try starting here. This is of course an illustration. The NFA doesn't actually have, it's not sentient, but just for illustration's sake, and to make things slightly more entertaining for me. So the machine says, okay, well, how about I start at Q2? So if I start at Q2, then if I read a 1, well, I have to go back to Q2. Then if I read a 0, I have to go to Q3. If I read another 0, I go back to Q2. And then if I read another 1, then I stay in Q2. And so in this case, I'm in an accept state, right? So this was not an accept state, but this is an accept state. And so this is a successful computation, right? So it's a successful computation. Geez. Successful computation. And so since N has at least one successful computation, it accepts X. Right. So if there is some way for the machine to start at the start state, read the whole string, and end in an accept state, then it accepts the string X. If there is no way for the machine to start at any of the start states, read the entire string, and end in unaccept state, then it doesn't accept the string. So in other words, it rejects it. So what's an example of a reject? Let's do that quickly. Well, so suppose the input X is 1, 0, 1. This time I won't trace it out. Let me just use the pointer. So if the input is 1, 0, 1, right, then I might start at Q0. If I read a 1, then I go here. Then I read a 0, so I stay in Q1. Then I read another 1, so I go back to Q0. So that's a fail, right? So let's try the other one. I start at Q2. I read a 1. Then I read a 0. Then I read a 1. I stop at Q3. That's not an accept state again. That's another fail. In both cases, I failed. So that's a reject. So then the input X is rejected. Okay. And so in general, N accepts a string X if and only if there exists at least one successful computation, right? There could be more than one. And so by successful computation, what I mean exactly is that N starts at a start state, right? There could be more than one. Right, so A start state. It reads the entire string. So the reason why I'm emphasizing entire is because you'll see in a second that it's possible for the machine to read part of a string and then end in the accept state, but because it hasn't read all of the string, it's not an accept. So that's why I'm emphasizing that N has to read the entire string. So N reads the entire string X. And finally, N ends in an accept state. Okay. So that's what it is sort of at a high level. And now we've seen one example of an NFA. A question for you here is, what do you think the language accepted by N is, right? So the language accepted by N is all of the strings that N accepts. So all of the strings that have at least one successful computation. So what is the language accepted by the NFA N here? Sorry? Excellent, very good, very good. Okay, I was gonna give you a few seconds to think about it, but you didn't even need a few seconds. So yes, very good. The answer to this is, well, this machine, we already know what this does, right? This accepts the strings such that the number of ones is odd, right? And then this machine here, well, this machine keeps track also of parities, but in this case, it keeps track of whether it's seen an even or odd number of zeros, right? And in this case, because the start state, this start state is an accept state, it accepts strings with an even number of zeros. So then I have an OR here, and I have that the number of zeros of X is even. Okay, and an exercise for you, a very good exercise, is to design a DFA that accepts the same language. Okay. So this is a good exercise. And should I give you a hint about how to do this? No. Okay. No hint. All right. Question. Yeah. Ooh, that's a very good question. So the question was, is the NFA provided minimal? Ah, that's such a good question. The short answer is, in general, there isn't a notion of minimality for NFA. So in other words, it's quite plausible that I could make up another NFA with the same number of states, but that looked entirely different, and it would accept the same language. So this is something that NFAs have a property of, right? Their minimality of NFAs is not unique. It is unique for DFAs. So now I'm thinking whether it's a good question for a midterm, but yeah, anyways. No reaction to that, strange. But that's a very good question. Yeah. Any other questions about this? Yes, Marcello.
Do you have any special treatment of any kind of strings that are already accepted by the DFA? I mean, NFA?
Yeah, so this is a specific type of machine. We can talk about that later, like offline. Yeah, that's a good question. Yeah. The question was about NFAs, which for every possible computation are accepted. So we can talk about that later. One more question, yeah.
So is every DFA and NFA?
Wow, another very good question. The question was, is every DFA an NFA? Well, what do you think?
Yeah.
You think yes? Why do you think yes?
Because the only thing that makes something NFA is that it has 0 or more choices,
Yeah.
and DFA has.
Very good. Excellent. Very good. You guys are so brilliant. It's amazing. Yes, very good. Excellent. So the question was, is every DFA an NFA? The answer is a resounding yes, because the definition of NFA is you're allowed to have choices. A DFA just has a single choice, right? So that's okay. It's got one choice. It's good enough. Right? Excellent question. Okay. Very good. Let's do another exercise about designing NFAs because they're on your assignment. Okay. So this other exercise is going to be design an NFA-N such that the language accepted by N is a set of strings over 0, 1. The alphabet 0, 1, where W ends in 0, 1. So of course, as someone just pointed out, I could just make a DFA, and then technically speaking, I'd be answering the question. But in your assignment, I do say something like, you must use non-determinism, right? So this is very important. I say in the assignment, so in assignment 1, I say you must use non-determinism. And so in that case, I'm forcing you to have some state that has to make a choice, right? So it can't just be a DFA because you already practiced doing DFAs in question 3, right? Okay, so how am I going to do this? So this is a nice place to introduce this other concept for NFAs, which is that they're kind of like these machines which guess and then verify their guesses. Okay, so what do I mean by that? So suppose in this case here, right, I have the language that I want to accept, and the strings in this language must end in 0, 1. So for instance, it could be 0, 0, 1, 0, 1. Right, so this is a valid string. It should be accepted because it ends in 0, 1. And so one thing you can think about when you design an NFA is that, for instance, in this case, it can say, well, I'm just going to guess where the last 2 letters are. So, suppose it guesses here, right? It guesses that it's there, and then it's just going to check, right? So then it checks, is my string ending in 0, 1? Well, no, because I have more string here, right? So that means that my guess was incorrect. So then, okay, it says, all right, well, let me try again. So let me guess that this is the end of the string, right? The last 2 letters of the string. So it guesses that this is the start of the 0, 1 that's ending the string, and then it verifies its guess. And then in this case, it finds out that its guess was correct, and that leads to an accept. So that's the intuition. What does that actually look like? Well, I have my start state Q0. In this case, I only need 1. My start state Q0 is going to be the thing that's going to be guessing. So my start state Q0 is going to be guessing. So it'll guess that the string has 2 letters left. So it's reading the string, and then it's like, oh, okay, I think I'm at the last two letters of the string. Let me check that they end in 0, 1. And so then to check that, right, you need to read a 0. And then you need to read a 1. Okay. And so if the guess was correct, right, if you guessed at this point here, then you'll have read all of the string here, and then you'll finish reading the string 0, 1 through this computation. But let's sort of work through how this machine actually intakes an input string. So maybe I'll take questions after. Okay. So how does this machine actually work through an input string? So suppose it receives as input x is 0, 0, 1. Okay. So suppose, that the machine, well, not suppose, it does start at Q0. And from Q0, it says, well, I'm reading the 0. This probably isn't the before last string. And so I'll stay in Q0. So it reads the 0 and it stays in Q0. And then it says, well, you know what? I don't even think this string I'm reading now is the before last string. And so I'll read this one too. Right, I'll read this one and I'll stay in Q0. And then, well, once it's at Q0 and it's reading a 1, well, it doesn't have a choice. It's going to have to take this transition again. And so it stays in Q0, but now it's finished the string, right? So in other words, what happened is that it guessed incorrectly. What it guessed is that essentially it never guessed that it was at the before last string. And so it missed its chance and it just remained at Q0. And so that's a fail, right? So in this case, this could be sort of saying that the machine was too patient. So the machine was too patient. Okay. So what happens if the machine is too eager? Okay, so it's too eager to accept. So it starts at Q0 and it's reading the 0 and it says, you know what? Actually, no, I think this is the before last string. So let me just verify that it is and that it's the start of the 0, 1 ending. Right? So it reads the 0 and it goes to Q1. Then it's at Q1. Right? It's at Q1 and it's supposed to read a 0. But what happens? Right? At Q1, there isn't a transition for 0. And so the machine jams. So the machine jams. Jams. So, whoops. If the machine jams at Q1, that means that it can't keep reading the string. And moreover, it's not even in an accept state, although that doesn't really matter because the machine has to read the entire string. And so because it jams at Q1, it doesn't read the entire string. And so again, this is a reject. Right? So in this first case, the machine was too patient. In the second case, it was too eager to accept. Right? And so what happens if it's, just right? So it reads this first symbol 0 and it stays at Q0. So it reads the symbol 0 and it stays at Q0. And now it guesses correctly. So it guesses correctly that 0 is the before last symbol. So it reads the 0 and it goes to Q1. And then it reads the 1 and it goes to Q2. So what's happened is that it's read all of the string. It's finished in an accept state. And so this is a successful computation. So then X001 is accepted. Okay. Let's go. There was one person who had raised their hand first, but I forget. I think it was maybe Owen. Yeah. Yeah. General question, yeah. That's a good. Oh, I see. That's a good question. Yeah. Yeah. So the question here is, isn't checking all the possible guesses something that's super slow? And the answer is yes, absolutely. So there's two parts to the answer. The first part is that when you design an NFA like this is more sort of out of convenience because these machines are quite sort of compact to write time. we'll see in the next lecture that NFAs are actually equivalent to towers together. And so you're not actually gaining anything by getting it. The only thing you're really gaining is that this is a much more compact, which you guys are down, right? And so in practice, when you're actually trying to implement this in a computer doesn't actually guess, right? The computer is everything. At least the computer's not. And so what it does typically is it takes the NFA and it converts it to a DFA. And so once it converts it to a DFA, everything is uniquely determined, and so there's no head. And then the runtime is linear in the size of units. Yeah.
We have a string like 0, 0, 1, 0. Does it stop at Q2 or does it jam?
Yeah, good, excellent. Right, thanks for the question, because I didn't find, okay, good. So the question was, what happens if you're at X 0, 0, 1, 0, right? So what happens is, well, one possible computation is my machine reads this first 0, right? Then it guesses that this is the start of the 0, 1. So it goes to Q1, then it reads this 1, so it ends in Q2. But now what happens is because this guy doesn't have any transitions, it jams at 0, right? So the machine jams here. And this is very important, right? So this is very important. Even though Q2 is an accept state, because the machine has jammed, it hasn't read all of the string, so that's not an accept. Okay? So this is still not a successful computation. Yeah, good question, because that's very important. Students sometimes forget that if the machine jams, it doesn't mean that it's a reject, but it is. Yeah, it's a fail. So 2 more questions, Marcello, and then you.
If NFAs and DFAs are computationally equivalent,
yeah,
then is there anything we gain from considering NFAs as like just really thinking about them aside from the contented theoretical circular aspect of it, but then we get.
I'm not going to repeat the question, but I will say that NFAs are, like I just talked about, a nice way of conveniently writing down some machine that accepts a language. And we'll see in the next exercise that there's a particular language where had you drawn a DFA, you would have required sort of an exponential number of states, but an NFA only requires a linear number. So no, it's not what you said. Yeah.
When I get to that, for now, because it rejects some direct constraints both ways.
Yeah, I didn't hear the first part. I'm sorry.
Now, that sheet that built is not going to be like it's not within the ways.
Oh, no. This is a perfectly good NFA that works. Why? Because suppose I have a string that ends in 0, 1, right? Suppose I do. Then there is a correct guess, right? And that guess would be, you go through that string, right? Well, let's just illustrate this. So, you have some string that does end in 0, 1. And so there is a correct guess, right? The correct guess would be you gobble up all of the first part of the string, and then you go to the accept state. Wait, hang on. So if you have a string that doesn't end in 0, 1, right? So, for instance, this one, then whatever you do, it's either going to jam, it's either not going to get to Q2. Yeah.
Doesn't matter if sometimes the machine rejects a string it's supposed to accept as long as there's.
Yeah, good. Yeah, excellent. As long as there's one computation, then it's okay. Yeah. So I'll take more questions after this next exercise. Yeah. Okay. So I think this might be the final exercise of the class, but this is a nice one as well. So this exercise is to design an NFA that accepts the language thank you. The language over the alphabet AB, such that the strings are of length at least 5, and the fifth to last letter of W is B. Okay, so in other words, I'm considering strings over the alphabet AB. These strings have to have length at least 5, and the strings have to look something like, let's see, AB, B, A, B, right? So the fifth to last letter, so this is the fifth to last letter, is a B, right? And so of course, you'll notice, hopefully, that this is the same question as assignment 1, question 3, except that it's not the second to last, it's the fifth to last. And in this case, I'm asking you to do an NFA. So in fact, had I asked you to do a DFA, this would have taken you 2 to the 5 or 32 states, which is not something I'll ever do. So don't worry about it. Okay. But actually, it's a fun exercise. Well, I think it's fun to show that in general, the nth to last string being some letter requires 2 to the n states. I'll get to you after I solve it. Yeah. Okay, so how am I actually going to solve this? It's going to be a similar idea to what I was saying before when I'm guessing and then verifying. So I'm going to have my my start state, which is just going to keep reading strings, right? So it's going to keep reading strings, and then at some point it's going to guess. It's going to guess that the B it's reading is the fifth to last. So it guesses that this guy is the fifth to last, and then what it needs to do, it needs to check that, right? So it needs to check that it has 4 more symbols left, and exactly 4 more symbols left, because that by definition means that the B was the fifth to last letter of the string. Okay, so then to do that, it just has 4 more transitions. And then this is an except state. Okay. Question, yeah. Yeah. Shrink this even more? This is pretty shrunken.
Yeah.
Oh, actually, that's it. Sorry to cut you off. There is this other type of way of representing languages known as the regular expressions. And the regular expressions kind of give you something slightly more compact than this. So yeah, and they're equivalent to NFA and DFA. But we'll see those in a week from now. Yeah.
And for the assignments.
Yeah.
If you technically just arbitrarily add get ends to that DFA to make it an NFA.
Not for the assignment solution. But yes, in theory, if you had, yeah, but yes, yeah. Yeah.
I think someone was asking about the applications of DFA versus NFA, and I was wondering, like, a DFA, I see a direct relation to mapping it to a circuit, let's say. But for an NFA, I was wondering if that can translate to some kind of circuit for a computer, or if it's more like quantum computer.
Yeah, that's a good question. So the question is about the sort of practical implications of NFA. There's one immediate thing that it's useful for, and that's just like storage. Because suppose you have some very complex language you want to recognize, you can create something like this, and this is typically, you know, it's not going to require that much space. So you can like save it to some hard disk, right? So you have it somewhere, and then you're supposing that you have a lot of time. And then you just run the conversion algorithm when you need to, you convert that to a DFA, and then you get a quick language acceptance. So yeah, in terms of circuits, not quite something that you use, because circuits typically, unless you're talking about quantum stuff, in which case you talk to float, you don't really want to talk about, like, you don't want to be like, oh, I don't know where this voltage is going to go to. That's probably not good. Yeah. Yeah. What's your question?
Like NFA, you just define it into subscriptions, you can make an NFA and then.
Yeah. Yeah. So for instance, in your assignment, there's a question about designing an NFA which has the substrate A, B, A, B, A, B or something. Designing a DFA for that would be a real pain in the something. But designing an NFA for that is actually quite simple. Yeah. Okay, last question. Oh, yes, yes.
I just quickly want to verify.
Yes.
So, no, we can have like extra spaces, like next to the definitions, but in this control, we can read the not specified with the position. Like in the last one.
Yeah.
You can ignore the letter.
Yeah. So in other words, a state could have, and we'll see this when we talk about NFA formally, it could have as the output of its transition function the next step. Yeah. Good. Okay. So how much time do I have? I said 4 minutes. Okay, 4 minutes is plenty of time to do something. You said smiling. Okay, so the last thing I want to do is I just want to quickly introduce the formal definition of NFA, and we'll start from there on Thursday. So the useful thing about NFAs, like I talked about before, is that they're sort of computationally equivalent to DFAs. But to show this formally, which we'll do on Thursday, you need an actual sort of rigorous and formal definition of NFA, similar to the one we gave for DFA. And so that's what I'll do here. So formally, the definition of an NFA. So an NFA, N is a 5-tuple. So it's similar to a DFA, where each of these elements of the tuple are as follows. So Q is the finite set of states of the machine. I think when I defined DFAs, I didn't explicitly say that they were finite, but they are. And so in NFAs, I'm explicitly saying that they are finite, but that should be sort of taken for granted in the DFA. Sigma is no different from the sigma in DFAs. It's the input alphabet. Delta is the transition function. So in this case, the transition function is the sort of workhorse of the machine, very similar to DFA. Now, except that for now, in this case, if you're at a state, right, and you're receiving some input, your machine can return a set of states, right? Because the set of states is what's sort of this, is this implementation of possibilities, having multiple choices. And so what this looks like formally is that the transition function takes a state, takes some letter, and then returns a subset of Q. So in other words, if this is P, and from P, I can do this, then delta P of A is the set containing Q1, Q2, and Q3. The other thing is the start state. So notice here that this is a capital S. So it's a capital S because we're going to use it to denote a set of start states. So this is a set of start states. So S naught is a subset of Q. And the last thing is what F is. F is a set of accept states. So it's also a subset of Q. And in the next class, we'll talk formally about how we can take this transition function and talk about the extended transition function, very similar to how we talked about delta and delta star. And that'll be the mechanism by which we talk about language acceptance and how we talk about DFAs and NFAs being equivalent. Thank you very much. See you Thursday.
Question. This might be stupid,
No,
but
no stupid questions.
like could an NFA be designed in a way that results in a success for more than one compound?
Yeah, absolutely. Yeah, it's possible.
Okay.
Yeah.
So like it doesn't stop when it reaches like one.
No, you can think of it as it's just trying all the possible choices.
Okay, so it
Yeah.
won't like stop if it gets the.
No.
string,
Imagine that it's doing everything. So it's,
Okay.
yeah, so it's
And then, like,
inefficient.
Like, does it store the information anywhere or like,
Yeah, it's still, the states, so these states are still used for memory, right? So
Right.
like this state is, oh, I think I've just seen the fifth to last B or
right?
the fifth to last symbol.
Yeah.
And now I'm gonna check that I have 4 letters left.
Okay, so if
So it's still encoding some piece of information.
okay, but like, it might be the case that it will end in a reject state just because it's trying all the functions.
Yeah, exactly, yeah.
Okay,
And that's okay. As long as there's one computation which is successful, then
right.
that's fine.
Oh, that is going to.
Yeah, yeah,
That makes, thank you.
yeah, no problem.